So are any of you also seeing the video lectures? नहीं देख रहे हो? Classes attend करो तो ठीक है. But some of the video, I think it's updated till about 1 or 2 lectures back. And the site has already been sent to you, put there on the Moodle. So, okay. So last class we finished our discussion on grid turbulence. Okay. So now today we will look at pure shear flow. And this will be a short discussion, probably about 10 to 15 minutes, because, but one thing I think all of you has, everybody now submitted homework too. You have to submit today, but you have done it, that means. तुमने भी आज करना है, ठीक है, तुमने कर लिया पर. So now you have gone through the grill of deriving the Reynolds stress equations. And you have done it in various forms. Like assignment 2A was basically just the Reynolds stress equation. Assignment 2. 2A was another form of it where some terms had to be manipulated. And similarly with 2B, that some other terms had to be manipulated to get it in different forms. And this exercise, I think if you have done it yourself, you will realize how complex it gets when we look at the Reynolds stress equations. Because there are so many equations and then new quantities which come in. So now what I will do is, in some of these, we will refer to the Reynolds stress equations and I will put in the simplified form. So the actual form, sometimes you will have to see how under these conditions it simplifies to this form. So I will not be exactly for everything going in the class showing you why each term is 0. So that you can probably check by yourself. You have, but if you have derived the whole thing yourself, you know. Another thing you should be comfortable, and this is for the exam also, with the tensor notation. I, J, K and summations, etc. I will not question you on the using of epsilon I, J, K. I will get epsilon I, J, K today. So I will not question you on, there's another formula which is when there are two epsilons together, it changes into delta functions. I will use that, but I will not question you, because I think I'm getting down too much tied with the nitty-gritties of the equations and tensor algebra, and in that physics is sort of getting a backseat. Okay, so that's what we'll do. So today, let's quickly see what happens in pure shear flow. Now, what do we, the grid turbulence, what did we have? U1 was there and it was a function of x1. Shear flow means there is always a shear. Shear, if you have to think, is something which is slipping. So that means U1 will be a function of x2 as opposed to grid turbulence. So here what we have is mean of U1 is a function of x2 and mean of U2 and mean of U3, they are 0. And if the flow is stationary, sometimes we may say steady in the mean sense instead of stationary. So then d by any averaged quantities time derivative will be 0. And in this case, in pure shear flow, the flow is homogeneous in x1 and x3 directions. What does this mean? This implies d by dx1 of any mean quantity is 0 and d by dx3 of any mean quantity is 0. So all statistical quantities are follow this. So now if I look at mean of Sij, this was what? Half of dy by dxj I don't need to put this second bracket, but anyway. Okay. So now, if I now try to write the components of Sij, which components will be non-zero? So now dui by dx1, du1 by dx1, is it 0 or non-zero? x1, d by dx1 is 0. D by dx3 will also be 0. So that means the only thing which will count is d by dx2. And I will have to be 1 in this one, and in this case I will be 2 and j will be 1. So the only non-zero component of this will be S12. S12 and S21, that's right, because S12 and 21 are equal. So the only non-zero components is non-zero component of mean of Sij will be S12 and S21, and they will be equal to S12 and S21 will be equal to du1 by dx2. Okay, na? Because its half is there and there are two sums, so we get this. Half ही होगा, एक मिनट रुको. S11 will be equal to dui. नहीं, I और j दोनों 1 रखोगे ना, S12 रखोगे. Half of du1 by dx2, you have to sum over j and भाई S12 is equal to I को 1 रखा, j को 2 रखा, j को 2 रखा तो 0 हो जाएगा, हाफ. Okay. So now in this case, the kinetic energy equation we had written, let me write the full form. The turbulent kinetic energy will look like dk plus uj, I am writing the full one so that we can see how to simplify this, is equal to minus So this is the full kinetic energy equation, and this I am not doing in the class, but I'll just show you one or two terms. Partial k by partial t. Just copy this down first. Let me then. ये पहले लिखा हुआ है अपने notes में. This is nothing new. So partial k by partial t will become 0 because all averaged k is an averaged quantity. Okay, and then this term u1 partial k by partial x1 will be 0. u1 is not 0, but partial k by partial x1 is 0. And then u2 and u3 are 0, so this whole term will become 0. This is how you will have to analyze this. And that's what I'm saying. Maybe I will give you, simplify this for this case. And you should be able to do it for a more complex case also. Expand it fully. Okay. So similarly, each of these terms you simplify, in the final, after simplification when we do it, what we get is, because now in this d by dxj, the only j which will count will be 2. 1 and 3 are 0. So we will put everywhere where j is 2 is what we have to put. And if something else is repeated, you have to sum over that. So for example, here I is repeated, so there will be summations on I. J, only non-zero j will be 2, And then if you get somewhere a mean of U2 or mean of U3, those terms will become 0. And similarly in this Sij, we only know it will be 1 and 2. When I is 1 or and j is 2, so here we'll have to just accordingly simplify. Prime में everything is non-zero. But then average quantity, जो total average है, उसका x1 and x3 derivatives are 0. So now this term will stay as it is because there is no derivative. So this will be a full summation of 9 terms. And even Sij itself has half and half. Actually, this probably is more complex in this form than if we just took the dissipation as d2 ui by dxj dxj. That may have been easier. But anyway, so this term will have all the 9 terms here. No derivative here. So that, but in this term again the same thing. Sij, there will be some 0 component. So according to that, this will, but there are no derivatives. Wherever you have a derivative of an average, so there you will have only non-zero if it is something like x2r. Okay? So when we expand this, and this you can check up at home. If you don't, if there's an issue, you ask me. Oh, sorry, I should have पहले first term लिखते हैं. ये आएगी term, but I'll write it in the same order. Minus partial by partial x2 of 1 over rho So this last term I have written it as epsilon. 2 nu Sij prime average is called epsilon. That's what we have called. So this is what we have. So here what we do is we neglect new term the transport term has 3 terms. Transport is always part of the derivative term. So here there are 3 terms. This term is neglected because its order is less than these. And this we have discussed earlier. So we neglect the new term in the transport term, and all other terms of order all other terms means this term, these terms and epsilon, everything is of order u prime upon L, or I write it as u prime RMS cube upon L. So all the retained terms are of this order. Now that is the only thing we are getting from this kinetic energy budget. This is the K equation. Okay. So this tells us, okay, this term is the only term which is small order. All these other terms have balance. So therefore, if you have to solve this equation or you have to get anything out of it, you'll have to then account. We don't have anything for u2 prime p prime. I don't have an equation. I don't have an equation for ui prime, u2 prime. So if I have to solve either, I have to write these terms in terms of something else. And this is what we call as turbulence modeling. And we will do that toward the end of the course. That how do we model out these terms. Okay, this term is negligible. This term, if I'm writing an equation for u1, u2, then this term is there, mean is there. So these terms don't bother me. For dissipation, as you will see, when we come to modeling, we'll write another equation. So therefore, this is how we simplify. Now, as of this, as of the course, as of now, I will leave the equation at this stage. But keep this in mind when we come back to modeling, that some of these terms were something about which we don't know anything. All we know is they are of the same order. But that doesn't help us if we have to solve the full equation. And that is why you'll realize as we go deep down the course that turbulence becomes very, very complicated. As a subject, how do we tackle it? Because the equations, even under this simple form, actually the equations are much more complex. We only took mean of u1 as a function of x2, and all other averages are only a function of x2. Nothing a function of x1, x3 and time. If they would also have been there, the terms would have been many, many more. So that's what then we try to address, how to take care of this. But here some more physics comes in the problem. If we look at the equation, kinetic energy is what? u1 prime square plus u2 prime square plus u3 prime square by 2. If we look at the equation of u1 prime square alone and put these simplifying assumptions, what do we get? Now, what is the equation for u1 prime square? You have done that. You have derived the equation for ui, uj. Now you don't sum up. If you sum up, you will get the equation for k. If you put I is equal to j. Don't sum up, put I is equal to 1, put j is equal to 1. That's different from putting I is equal to j. Okay? So, if we now look at that big equation which you have derived, and that is why I referred to that at the start of the class. Look at the equation for u1 square by 2, u2 square by 2, u3 square by 2 separately and apply these simplifications. Simplifications are what? D by dx1 is 0, d by dx3 of all average quantities is 0, d by dt is 0. When you do all that, let me now not go through that detail. If I start going through it, it will take me another 1 hour to do that. So and there is some physics which we are getting, that's why I am discussing this. So if we write the equation for, so we write and simplify the equations for u1 prime square, u2 prime square, and these equations give me the one component becomes 0 is equal to wherever the prime has been forgotten, just add it. So these are actually equations not of u1 square, but of the components of kinetic energy. So they have been divided by half. And the 3 component will give you 0 is equal to 1 over rho p prime du3 prime by dx3 minus d by dx2, and in this case we get we get an equation of this form. No. नहीं सम्ड ओवर नहीं है, यही मैं बता रहा हूँ इसमें. See, these equations are simpler to write because all you have to do is there's no summed up था k वाले में. This is only for the equation for u1 square, mean of u1 square. So that means you put I is equal to 1, j is equal to 1. You don't sum over. See, there's a difference between u1 square, u2 square, u3 square and ui. When you write ui, you have to sum over I and j. So that means wherever you put I is equal to j, because there's a repeated index, there's a summation. But when you have the equation for u1, u2, u3, actually these are, you just put I is equal to 1, j is equal to 1. On the right hand side, all those terms are there. P11, R11, epsilon 11, etc. etc.
काइनेटिक एनर्जी स्क्वायर्स के सम के मीन को डिफाइन करेंगे या
इन तीनों का सम जो होगा u1 प्राइम स्क्वायर प्लस डिवाइडेड बाय 2 प्लस u2 प्राइम स्क्वायर का मीन, मतलब मीन ऑफ u1, हाँ मीन्स का सम है, नॉट सम्स का, बिकॉज हाँ
क्वांटिटी का मीन इज नॉट इक्वल टू द मीन का सम.
हाँ स्क्वायर्स है. So इन तीनों का सम विल गिव यू काइनेटिक एनर्जी. नहीं वो हो जाएगा, एक मिनट रुको, u1 एक सेकंड, u1 प्राइम स्क्वायर है, u2 प्राइम स्क्वायर है, u3 प्राइम स्क्वायर, इन पूरे का मीन लोगे दैट विल बी इक्वल टू सम ऑफ मीन्स. हाँ स्क्वायर है ना, स्क्वायर है. हाँ
Why do we have epsilon by 3 here? I'm assuming it's because
we have assumed isotropicity here.
okay, but
Otherwise it should be epsilon 1 1, epsilon 2 2, epsilon 3 3.
that would be also form
टू न्यू SI J तो सब, हाँ उसमें I और J.
The problem here is that when we write for two components, because
हाँ.
J is fixed at 2, right?
Yeah. So it will actually this will be epsilon 1 1, epsilon 2 2, epsilon 3 3.
Epsilon 2 will be 0.
Epsilon 2 2, why would it be 0?
So because we have S prime ij, j is equal to 2.
हाँ.
So when I'm fixing I equals to 2, we have S prime 2 2 and
So S prime 2 2 is not 0, it's prime. Fluctuations तो सबका फंक्शन है.
ये कंप्लीटली also divided del u2 prime by del
नहीं बट केवल S2 प्राइम नहीं है ना, एक और टर्म मल्टीप्लाइड है उससे, उसका मीन है. इट इज SI J, इट इज ऑफ दैट फॉर्म.
No, that is a multiplication of like one S prime with another S prime. Right?
तो देख लेना, क्योंकि see what happens is in these equations, actually in uij equation you get epsilon ij, not epsilon. So now there will be an epsilon 1 1, epsilon 2 2, epsilon 3 3.
But what I'm saying is when we write S prime 2 2, S prime 2 2,
हाँ.
I'm just saying that S prime 2 2 in itself should be 0. Right?
No, why should it be 0?
So because S prime 2 2 is del u2 prime by del x2
हाँ.
plus del u2 prime by del x2. Now
हाँ.
del u2 prime by del x2 in itself should be
Why should no प्राइम का 0 है भाई? It is नहीं, कंटिन्यूटी से केवल du2 प्राइम क्या है? इट इज इक्वल टू माइनस du1 प्राइम बाय dx1 माइनस du3 प्राइम बाय dx3. भाई कंटिन्यूटी क्या है? कंटिन्यूटी इज partial u1 prime by partial x1. This is continuity. है नहीं तो ये इस मीन तो अब पूरे का, पर अगर यहाँ पे du2 प्राइम बाय dx2 है, इट इज बीइंग मल्टीप्लाइड बाय अनदर सब टर्म. अगर केवल du2 प्राइम बाय dx2 का मीन आई एग्री इज 0. But this is product of two terms. So you'll have to look at it. This form comes into this. It may take you some working to get, and possibly here to make it epsilon by 3, we have assumed that epsilon 1 1, epsilon 2 2, epsilon 3 3. The dissipation is isotropic, that it is in this form. All these three are equal. But from here, नहीं वो एक 2a 2b में there was this form used for rij and pi ij. So one of those forms is like this. See, उसमें वो continuity equation use करके we just change it like this. भाई देख लेना, मतलब I think let me not get stopped by this because the homework में I have the homework with me here. There is a term, we write it as ui prime dp prime by dxj plus uj prime dp prime by dxi एक form है. And also then later on we say that t क्या है जी, the pressure term को हमने रख दिया 1 over rho ui prime p prime delta j के, तो इन फॉर्म से ये आ जाएगा. Finally, we have used this form Pij plus Rij minus epsilon ij. So Rij जो देखा है, what is Rij? Rij was written earlier. In Rij when we wrote, Rij कहाँ है ये रहा, Rij में we had P prime du prime by d. Actually the equation is dp prime by dxi times u. But then we wrote it in this form. Rij is P prime du prime by dxj. So that is what will give you this form. When you use, that's what I said, there are three forms. So when you look it in the Rij form, you get it like this. So just see, the point which is being tried to made here is that when we look at the equation for one component, two component and three component of kinetic energy, all the three components of energy are there, none of them is zero. It is not that u2 prime is zero, u2 prime, that kinetic energy of this component is zero or this. But what we find is the production term is there only in the one component. In the other components, there is no production term. Okay? So let's see this. So from here what we observe is that production term only in the equation for u1 prime square by 2. Because S1, 3, S2, 3 are 0. So there is no production term there, what we called as production. But we also realize is mean of P prime du1 prime by dx1 and this is where I am glad you brought up the continuity equation. This is 0 because what I can do is I can take the continuity equation which I have written here, multiplied by first P prime. This is all 0, sum of all these, multiply each term by P prime, and then I take average. So that means sum of these is 0. Okay. Now the reason why why I am working out this is, that means if all these sums are 0, if one of these is positive, two have to be negative. So at least one of them will be positive and others will be negative. Because this is 3, sum of all of these is 0. Now what we find is, so in this equation actually what happens is, this term actually is negative, P prime du1 prime by dx1. So this term is positive, production is positive, we know u1 prime, u2 prime is generally negative, S12 is positive, so this term is positive, this term is negative. So, and this term being negative makes these other two terms positive. Okay? And these two terms then act as the source for u2 prime and u3 prime. See, if there is no source in u2 prime and u3 prime, they will go to 0. But we find that the components are there, but so therefore this becomes the production term, and the pressure term is just distributing the energy from one component. Mainly it comes in the one component first, but the pressure term distributes it to 2 and 3, and that's why we call it as the redistribution term. When we do the full second order equation, Rij, what I call the R, comes from the fact that it is called redistribution term. So therefore, in this equation, production takes place mainly in one equation. But some of it is then lost to this term, which is negative, and this term being negative makes these two positive. So that is what acts as the source of energy, because these d by dx2 terms, these are only transport terms. They don't, they will redistribute things, but they will not produce. So this acts as, these two terms become the production term for 2 and 3. And also what one finds is that because the main production term is in 1, in such flows the u1 prime square is normally about double of u2 prime square and u3 prime square, because the production is mainly coming in the 1 equation. And from there it is getting redistributed to 2 and 3. Pardon? Why is this negative? Well, it happens to be negative when you look in the experiments again. This all comes from data. There is no mathematically, so it's a correlation between these two. Maybe if one tries to, we'll try to give some of these explanations when we go to vorticity, but it's found that this term is negative, acts as a sink, and these two terms therefore get their production. हो सकती थी, पर ये दोनों ऑलमोस्ट बराबर होती है, क्योंकि 2 and 3 डायरेक्शन में थिंग्स आर ऑलमोस्ट द सेम. 1 डायरेक्शन में ऐसे हो रहा है. हालांकि 2 की भी एक प्रेफरेंस है बिकॉज ऑफ द d by dx2. So there could be some change, but it's found again, this is data which is one is talking of, that these two terms act as the production term, and that's why we just did this. So the pressure तो वो है ना, pressure always is isotropic. The way we have defined pressure, it is always the same in all directions, because the extra part of pressure is actually what comes in u1 square and u2 square and u3 square. ठीक है? Yeah.
I agree, but I'm taking a small segue. This is modified pressure, right? This is not the actual pressure. So this contains that
Gravity.
potential term. Now that only has a k cap term, right?
That will come in the mean,
So
not in
that
primes.
makes it sort of
No, but that will come in the mean. It will not come in the
prime.
when you prime में नहीं आएगा. So ठीक है. So what will so there is no production term component what we find, what is observed is, I'm writing what I've just said, P prime and acts as a to redistribute energy through P prime du2 prime dx2 and P prime du3 prime by dx3 respectively. And in most shear flows, again this is all empirical data or experimental data, mean of u1 prime square is about double of, I should say, of the order 2 u3 prime square. So the one component is larger compared to 2 and 3 components, and that is because the main production comes there, and this the sink is in these terms. Okay. थोड़ा सा absorb कर लो इसको, then we move on.
तो फिर इसमें जो आपने हमें पहले बताया था तो कि वो एक स्मॉल स्केल पे टर्बुलेंस लेते और उसके बीच में एक पार्ट काट के घुमा देते हैं तो वो
Isotrop. No, वो जो था, that what I said was towards the extreme small scales when turbulence becomes isotropic. So this part is at a larger scale because that is why, in fact, if you remember in all these equations we have there's a there's a viscous part of the transport term and all, we have neglected all those. So while this dissipation is of the order of u prime cube over L, but that acts as a redistribution term again. But that what we talked of isotropic, that is at very, very small scales towards, and that's why we say turbulence is universal probably in those scales. And some of that we will also show now from the next type of arguments which I'm going to use, and that will be basically, we will try to now physically look at vortex dynamics. So first let's define omega I, we will call as now somewhere I think even if you read Lumley's book first chapter, they say turbulence is vortical. It has high vorticity. So now we want to, having seen all these equations, we want to see what role does vorticity play. And for this, our approach will be two-sided. First, we will look at the velocity equation, which we have done. And we will try to convert things in terms of vorticity in that equation. Some of this you may have seen in your first course, but I'm assuming you have not done anything. So we'll derive that. And we will show how vorticity comes up even in the Navier-Stokes equation. That will be the first part. And then what we will do is we will derive an equation of vorticity from Navier-Stokes equation, which is again straightforward because all you have to do is take del cross of the Navier-Stokes equation. Okay. So now let's see. So omega I is instantaneous vorticity, and how do we define omega I? Now for a change, I could have defined it as capital omega I also, but I'm taking it as omega I small. Instantaneous, what we had done was taken capital signs. So it could have been capital also, but the reason is the fluctuating part in the book has been omega, small omega, so I'll use small omega prime. So I'm using instantaneous vorticity as omega I. And Lumley's book also uses the small omega with a hat. So then there will be lesser confusion. Now, vorticity is defined as del cross u. U is the instantaneous velocity, which we have shown by capital U. And in tensor notation, this becomes epsilon ijk. Now, epsilon is the alternating tensor. Now, I don't, how many of you have seen this before? तुमने नहीं देखा कभी? ये epsilon ijk कहीं नहीं देखा? तो फिर हाथ क्यों नहीं उठा रहे हो भाई? मतलब देखा है मतलब पता तो किसने बिल्कुल नहीं देखा? I think all of you have seen it. Okay. So that sort of, now how do I write it? Del cross u. So whenever we have a cross product, we put epsilon ijk. The first index is the index of the final vector, which is I. The second index is the index of del. And the third index is the index of the vector. So that means del means d by dx something. So how am I going to write? duj by dxk or duk by dxj? Del uk by del xj. Because here in epsilon ijk, order is important. Okay? So I'm going to write this as epsilon ijk partial uk by partial xj. Is everybody, you may have seen this, at least advanced fluids का course किया है तब तो किया ही होगा, but otherwise also this is how we write del cross E. Okay. Now, other thing we will do is, we'll use this later, that if we average it, this omega I, this is instantaneous, so this we will write it as if we average the instantaneous vorticity, it will be mean vorticity plus the fluctuating part. That means this is the symbol for mean. I could have used mean of small omega I. Okay, but let's. So this is, and this is again so that we are not too different from Lumley's book. किसमें मीन में एंगुलर ब्रैकेट लगाते ना हमने तो अच्छा नहीं सॉरी हाँ ब्रैकेट की जरूरत नहीं है यू आर राइट दिस द मीन वोर्टिसिटी दिस नो ब्रैकेट इज नॉट नीडेड नहीं बट मीन ऑफ यूआई लिखते हो तो मीन यूआई तो लिखते हैं ठीक तो है इट शुड हैव बीन मीन ऑफ स्मॉल सो नाउ सो मीन ऑफ इसको स्मॉल ओमेगा आई कर देते हैं ठीक है ओके दिस इम्प्लाइज मीन ऑफ ओमेगा आई यहाँ पे आई एम प्लेइंग दिस गेम ओके बिकॉज बाद में हर जगह इन लम्बलीज बुक ही यूजेस यूजे कैपिटल ओमेगा सो आई जस्ट मीन ऑफ ओमेगा आई है
इतनी अलग अलग नोटेशन की फॉलो करते
इतनी अलग अलग क्यों फॉलो करते हो
एक ही चीज लिख दो उसको ही मीन लगा दो उसको ही प्राइम लगा दो बेटर है
तो मतलब तुम कह रहे हो इसको नहीं मैं इसको हटा के केवल ओमेगा आई कर सकता हूँ
आप वो भी कर सकते
वो कर सकता हूँ बट फिर क्या होगा क्योंकि वो बुक में तुम फॉलो करोगे तो थोड़ा अलग है वो बुक में हैट वैट लगे हुए हैं इंस्टेंटेनियस के लिए आई डेंट वांट टू डू मतलब मे बी आई शुड हैव जस्ट फॉलोड और फिर पोप की बुक फॉलो करोगे उसमें अलग नोटेशन आता है उसमें ये वाला आता है मीन ऑफ कैपिटल ओमेगा आई तो सिंस आई विल बी फॉलोइंग दिस सो ठीक है तो बेयर विथ मी दैट्स ऑल आई विल से okay now if we look at duk by dxj this we can write it as half of again these are all instantaneous so there is no this is the symmetric part and this is the antisymmetric part of so that means skj is equal to half of and rkj is equal to half of rkj is equal to half of duk by dxj minus duj by dxk. So omega I can be written as epsilon ijk into skj plus rkj. You मैंने just these are all repetitions. I think we have done it many times. Now epsilon ijk is anti-symmetric. because epsilon 1, 2, 3, if you change the order, it becomes minus. There is any repeated index is 0 and skj is symmetric. So any time epsilon ijk is summed upon with a symmetric tensor, the result is 0. And this, if you don't know, you'll have to, I'll explain it to you afterwards, but I'm not going to spend more time.
वो एचजे को एसकेजे लिख देंगे तो चलेगा, पर आर तो जेके होना चाहिए।
नहीं वो आर के जे, क्योंकि अपना ये यू के बाय एक्स जे है ना,
तो हमने जे तो वही लिया अपना।
नहीं आर के जे यही होगा ना, यू के डी यू के बाई डी, हमने डी यू के बाई डी एक्स जे है, तो दिस माइनस यू जे बाई एक्स के, सो दैट फॉर इट इज आर के जे। आर जे के होगा क्या, एक मिनट को, यू के ने डी यू के बाई डी एक्स जे लिखा है, ठीक है, डी यू के बाई डी एक्स जे को आर के जे लिखा है ना, ठीक है। सो दिस इज इक्वल टू एप्सिलॉन आई जे के आर के जे. So this is one relation, that vorticity is equal to, this is basically RKJ is the velocity gradient tensor, it's anti-symmetric part. Now how many components does RKJ have? 3, because all the diagonals are 0. So there are 3 in this, and omega is a vector, so it makes sense that there are 3 components, so it should have 3 components only, because vector है दोनों को बराबर होना चाहिए. So this is 3. Now can I invert this relation? Can I conversely means, can I write a relation for Rij in terms of omega I? ये तो omega I को RKJ में लिखा है. So for that what I do is, and the final answer, let me show, it gives you, if I invert this, I get Rij is equal to minus half of epsilon ij k omega. Invert, इसका inverse relation करोगे. If you invert this, and I'll show you how this comes. So first let's just write the relation. So these are the 2 relations. How the anti-symmetric part of the tensor is related to the vorticity. Now how to do this? This omega k, for this what I can do is epsilon ij k omega k. This can be written as, sorry, equal to epsilon ij k. Now omega k I will write it as epsilon klm times rml, because omega k I use this relation, so I get it in this form. And here now this can be written as delta IL delta JM minus delta IM delta JL R sub ML. So this relation basically, this comes from summation of epsilons, when 2 epsilon come together. And so, and this now, this summation you should be able to do RML delta IL. So wherever the RL is there, it will become I, and M is there, it will become J, so it becomes RJI minus delta IM, so RI delta JL, क्या हो रहा है यार, minus RIJ. So this becomes equal to minus 2 RIJ, and from there we get Rij. Now this is just a matter of detail. I'm not, again, this is just to show that these 2 things can be related like this. How omega can be written in terms of Rij, how Rij can be written in terms of omega. if you have to. This is just the proof. It's not nothing to be questioned, too straightforward. Now another property, I'll just do some properties today of omega k. So first of all, when we have an irrotational flow, what does this mean? Omega is identically 0 in the flow. So omega k, the vector omega is 0. Now also what we realize is that omega has a property divergence of omega, whatever is omega, is always 0. Divergence of curl is 0, exactly. So this is A, this is B, they are not related. This is, if the flow is irrotational flow, implies omega k is equal to 0 for any omega. And this once again one can show from the symmetry of epsilon I. So divergence, that means omega, see continuity equation for velocity, this is like the continuity equation. Now for velocity, what are the conditions for continuity equation? Yeah, but when? Incompressible flow. For velocity, the condition becomes density is constant or the flow is incompressible. Then del dot V is 0. But del dot omega is always 0. Whether the flow is compressible, incompressible, just by the fact that omega is defined as del cos V, del dot omega will always be 0. It does not depend on what type of flow it is. It is just the definition of it. And this is something which I think you should all, we may need it. So, and in tensor notation, this will be written as what? How will I write it in tensor notation? Del dot omega. Partial by del xi. Partial omega I by partial xi is equal to 0. So we don't need to ever. Now in tomorrow's class, it's already one, we will start from the Navier-Stokes equation and we will derive, get to the vorticity terms. So I'm not going, so that means I'm only going to look at the velocity equation and I will somehow convert some of those terms using these things to vorticity, because there is a dy by dxj in the equations. So obviously those things can be written in terms of vorticity. And from there we will try to see what is the physical role of vorticity. Okay? That is what we'll do tomorrow and the next class. अब सब लोग एग्जाम का पूछ रहे हो, I will tell you on Wednesday कहाँ तक आएगा. आज नहीं बताऊंगा. स्टार्ट के 10 मिनट में मैंने ये कहा था तुमने होमवर्क कर लिया तो u1 स्क्वायर u2 स्क्वायर u3 स्क्वायर उसका डेरिवेशन तुमने कर लिया है. So that is what I said कि by deriving those equations you will get very complex